Just probably on the webpage.
I sent them in the I sent the solutions to the test.
Oh, yeah.
If you lost it.
I remember. I found that.
Oh wait, no, because yours is the other one, right?
Probably.
Talk to me. Oh crap. Talk to me right after again. I forgot that. Or can you send me an email and just say, dude, remember to send me those damn solutions, will you? Because I forgot. Okay, that's my fault.
It's all right. It's confusing the way it was set up. You know?
Yes, no, it's I just forget. Something. Let me hit autofocus there. There we go. All right. Okay, so our goal today is trying to understand circular motion. In particular, circular motion force problems. And there's going to be about 40 minutes of kind of boring stuff that's really technical that we kind of have to do to make sure we get this right. After that, we can start doing all the fun toys that you see over here. And we should have a good time at some point today, but not right away. And I like to start with this example here. Hopefully you can see this on Zoom. Just a ball on a string. There's a lot of physics involved in ball on a string. Maybe you got your mask? Thank you. All right. Ball on a string is going to help us understand this. Now, in this case, I actually want to analyze the motion of this thing as it's going up and around. And let's actually look at the problems on page 112 to start. I believe that's problem 647. Imagine we have this ball on a string. Okay. And just before the ball gets to the top of the circle, it's moving this way with some velocity, v initial. Just after the top of the circle, it's moving this way with some speed v final. And for right now, let's assume that the speeds are the same, but notice the velocities are technically a little bit different. One's going slightly up, one's going slightly down. Agreed? Now, I know from experience here, I'm just going to put a dot at the center of the circle. That's approximately the center of the circle.
Did you say they have the same speed and the same velocity?
Yes, they have the same speed, but not the same velocity, because speed is just how fast. Velocity is how fast and direction. Good? What is the definition of acceleration? You remember? What was the definition of it? How would you get acceleration from velocity? Let me say it that way. Yeah, change in velocity over change in time. You agree with that? Or dv dt, derivative. Well, now I'm going to work this a little bit. What is delta v? That's v final minus v initial. But I want to go even one step further. That's v final plus negative v initial. And that helps me understand my picture a little bit. Check this out. Delta v would be v final plus the opposite of this. So this one's pointing up this way. If I flip it, it's going down this way, right? Take a second to make sure you believe this. If v initial goes to the left and up, negative v initial should go to the right and down. Everybody cool with that? If I go tail to tip, v final plus delta v initial equals delta v. By definition, that should be delta v. Agreed? the change in velocity is downwards. It went from moving left and a little up to moving left and a little down. Do you agree the change in velocity was straight down? All right. What's that?
That seems kind of like at a left field, like thinking about it that way. But
Yeah, it's a little weird, right?
yeah.
But here's the point. Notice the acceleration should point the same direction as the change in velocity. Which way do you accelerate in this problem? Towards the center of the circle, and that's what's crazy. Isn't that cool? However, be careful. We have made an assumption here. The magnitudes of these two vectors are the same, or saying again, we're assuming constant speed. And this is going to be kind of the crux of why all these problems are a little bit odd feeling. Up until now, when things were moving at constant speed, what was the acceleration? Zero. Now we see if you're moving in a circle at constant speed, you have acceleration towards the center. Very different. Okay? We can take this one step further. Look at 6.48. What if the speed was changing somehow? Then it gets even more complicated. Let's say your V initial is this way, and your V final is a lot bigger over this way. So in this case, not constant speed. In fact, I would say you're speeding up. Do you agree? For some reason, maybe there's a rocket thruster on this, whatever. Right? Well, that's negative V initial. Delta V points that way. And maybe I'm going to actually draw this. I want to put the delta V down here. Okay, sorry, I just want to squeeze it in. For reasons that will become obvious in a second. The delta V is now off at some angle. So we see there's a component of acceleration towards the center. I'm going to call that A subscript C. But there's also a component tangent to the circle. And we see that the total acceleration, sometimes we'll even write the word total, is AC towards center plus a tangent to circle. Is everybody okay with that? And now think about this. Strictly speaking, this is okay to write it this way. This says I should be doing a vector. Well, this is the size of the acceleration towards the center, and this is the direction. This is the size of the acceleration tangent to the circle, and that's the direction. However, you know we do not want to have to write these words all the time. So towards the center, I want to actually go one step further here. I'm going to try and squeeze it in right here. My apologies if this doesn't work. Okay, if you're at some spot right here, this would be called R vector. That's a sloppy letter R. I apologize. This is going from the center to the edge. This direction would be called R hat, radially outwards. I'm going to go over this. All this stuff is defined on the previous page. So if you don't want to write this down and just listen, you can. But if you want to write it down, that's cool. We'll go over it one more time. Is that too small to be read at the back of the class? Okay, sorry if I wrote a little small. This means R hat means radially outwards. Well, what do you think towards the center would be then? Is it radially outwards? Is that the direction that means is radially outwards going towards the center?
Negative R.
Negative R hat. So that's the way you'll see it written in engineering books and such. Towards the center is called negative R hat, just what they use. Tangent to the circle. Does anybody have any guesses what they use for that? Think back to coordinate systems in your math class. When you go to polar coordinates, we use R and theta hat. Yeah. So R hat means radially outwards, so negative R hat means radially inwards. Theta hat means tangent to the circle, so in this case, that direction would be theta hat. Got it? And to be fair, we're not going to use these hats a lot. You'll see after we get done with today, but I feel it's important to say these words because they come up every once in a while. If you're a mechanical engineer, oh my goodness, you need to be good at that kind of stuff. But you can get good at it in a dynamics class. Is that clear? All right. You could obviously do 6.49 on your own. The main thing is a tan, you'll notice, could be pointing the other way. So now I want to make sure we're using these words correctly. So I'm going to go back to page 111 now and make sure we got all these different symbols dialed in. So go back to page 111. And even though it's probably going to bore you, I'm going to do it on the board with you. Oops, I want to go to board 6. So there's a lot of notation and symbols on here. We've talked about most of this. I want to make sure we get all of this information on here. Okay, so page 111. So watch out for problems if they say R hat or negative R hat. Usually we say theta hat is counterclockwise. In a math class, you know how when you're drawing a picture of a coordinate system in a math class, X, Y, and you could pick some arbitrary point out here. This would be R, and you probably know that the R vector is equal to X in the I hat plus Y in the J hat. You know what I'm talking about? And then, well, wait a second. If we put in an angle here, theta, this side, X, would equal R cosine theta, I believe. And right up here, Y would equal R sine theta. I know I do, kind of go over this a lot, but remember, this is the vector R. This is the magnitude of it. Remember, there's a difference between having the arrow and not. You know what I'm saying? Okay. Well, check this out. What is R hat? That's going to be R cosine theta in the I hat plus R sine theta in the J hat. All this divided by the magnitude. Well, the magnitude is R. When you drop this out, there's an R in every term. notice we get cosine theta in the I hat plus sine theta in the j hat. That's where I got that from. It's basically a fancy way of dealing with a rotated coordinate system, but now I can handle, you give me the angle, I'll tell you how much in the I hat and j hat are associated with outwards. That's kind of a useful thing. So far, so good? Now think about this. This thing is going into some sort of a circle like this, right? So notice this way is tangent to the circle. This way is tangent to the circle. So notice, tangent to the circle is going to have a negative I hat. Do you see that? Got a positive j hat and a negative I hat, at least in this quadrant. I'm going to do a little quick math for you here. If this is theta, what's left for this angle? 90 minus theta. Yep. This is a 90-degree angle. So if this is 90 minus theta and this is 90, what's left for this one? Theta. As a result, if you don't believe me, you can take your time and go through there or ask me afterwards. I don't want to spend a ton of time on this because I want to get to the answers. There's minus, I'll get out of the way. Basically, tangent to the circle, if you wanted to describe tangent to the circle in terms of I hat and j hat, you tell me the angle, we're done. Cool with that? So if you want to label that picture in your book, you see I've got all the stuff there. If you want to label those components real quick, you could do that. That way you can kind of, hopefully that makes sense, what's going on with the ball on a string if you have some angle. Any questions on that part? Okay, some more terms. If you see me write CW, usually that means clockwise. So instead of saying theta hat and negative theta hat, we're probably just going to say CW and CCW. You know what I mean? That way we don't have to actually use this that much. Again, this is hugely useful to engineers, so it's important to see it. We're going to use it in Physics 163 on occasion. So we will use it, but not very often in this class. We're going to use CCW and CW most of the time. And by the time we finish today, I think you'll realize how little we actually are going to use those, but I feel it's important to mention them. What else do I want to say? Oh. For my class, I try to use this called a double stripe T, right? A double line. So that's the time for one orbit, or sometimes we say for one revolution. If I have my ball on a string here, this time I'm going to orbit it this way, right? Notice the ball is, in this case, moving at constant speed, right? It's in the horizontal plane, right? When we spin it in the vertical, it speeds up and slows down. That's complicated. But if I just spin this thing this way, it's orbiting, and we could say the time to complete one revolution or the time to complete one orbit is called the period. Good? And instead of using a normal T, I use this double T. That's just what I chose to do. Capital T is tension, T is time, torque, all these T's, yeah. Okay. Get out of the way. Just a second. Tangential speed. Now you may be saying, dude, isn't that the speed? I'm going to show you something here. Imagine if I have this ball on a string, right? Now what happens if I change the length of the string, right? And if I start out with a really big one, and then I start pulling it inwards, do you agree the ball is not only moving tangent to the circle, but also closer to the center? Fortunately, we are not going to do those kinds of problems. We're only going to do problems where the radius is a fixed size. However, we're still going to call the speed the tangential speed just because in engineering applications later, you may also have a radial speed. You know what I'm saying? So just to set you up, we're going to try and get in the habit of using V tan, but we could just call this V for us because the radius is fixed. We don't have to worry about speeding up as it goes in. Okay. We've already talked about A tan, but I want to mention something more here. It's the time derivative of speed. And this is tricky. It's not the time derivative of velocity. I'll explain in just a minute. Oops. We also had AC. This is something that we're going to use called v squared over radius, the radius of the motion. Sometimes this is written as r omega squared, and I haven't told you what omega is, but I will in a minute. This equation is on your test equation sheet, so if you're worried that you got to memorize this, you don't. Okay. So in this case, remember the following. A is equal to the derivative of v. The acceleration vector is the derivative of the velocity. The derivative of the speed only, right? If you have a changing speed, then there's some component tangent to the circle, right? Your speed is always tangent to the circle. So if you're changing your speed, you must have an acceleration tangent to the circle. So far, so good? Just getting in your way. It does look. All right. Doing all right here. So, okay. There's another thing that a lot of textbooks use. They will use the symbol A subscript R. This would be radial acceleration. Outwards. And what happens here is R is equal to minus V over R. Depending on which textbook you purchased or are using or what web resource you happen to be reading that day, some people will say A sub R is negative V squared over R. Others will say AC is positive V squared over R. This is not a contradiction. I like to think about it this way. If we look at this one, R hat is radially outwards. I would like to think of a centripetal hat. Even though most people don't use this, we could call this towards the center, right? And to be clear, towards the center is minus R hat. So the fact remains is basically people choose to either put the minus sign here by saying it's size AC radially inwards, or they say it's minus V squared over R radially outwards. Now, I know this seems like a lot. Let me just say it this way. I'm going to run out of board. Let me go just a little bit. There we go. Can you still see that on Zoom, people? Is it still showing up? Kind of, you can still read the fonts? Okay. So here's the deal. In some books, A total is equal to AC in the minus R hat plus A tan beta hat. Other books, I will get out of the way, I promise. Okay. In some books, they'll use the symbol AR, and then you have to put the minus sign in because they call it plus R hat. In other books, they'll say AC in the minus R hat, so the minus is already there for you. Did that make any sense at all? It's just different notations, different books. Basically, if you're reading the books and you see sometimes, why do they put the minus sign with the V squared, and sometimes why do they not? It's probably this. Just stick an absolute value on it and know it points towards the center. If you're getting confused with this minus sign, stick an absolute value sign on it and know it points towards the center. All right. Is there anything else I need to say? Omega. I don't think I told you what omega was yet, right? Okay. Okay. I'm going to throw this in here. This is not on your exam equation sheet. Yet I argue it's so fundamental, you got to have this memorized forever. Okay? Omega is called your rotation rate. Think RPMs. So if you've ever heard of the term RPMs, or revolutions per minute, when you rev your engine in your car or something, you might see the tachometer register thousands of RPMs. That's basically the rotation rate. Okay? So there's something special about this. Omega is equal to 2 pi over the period in units of not RPMs, but radians per second. Think about the units, 2 pi radians per time seconds. We could convert radians per second to RPMs. All right, but this result is hugely fundamental. And we'll go into that more in, I think, 2 or 3 problems. Okay? What do you think? So far, so good? All right. Now, that's just terms. Remember that page 111 if you get lost. What I would like you to do is I would like you to look at 6.51, talk with your neighbor and talk it over. I'm going to get a simulation running and erase the board, and then we're going to talk about 6.51 when I finish that. Does anybody have any questions before I erase the board up here? You've got it all written down in there. Whatever, go for it. I'm going to erase the board to catch up. Okay. Talk as much as you want, stretch if you need to. Again, I'm just erasing the board really quick and I'll get the simulation fired up. If it doesn't make sense, talk to your neighbor. Just try to resist the urge to look at the answers, all right? Hopefully it makes it fun to talk. No racing. Pretty good. Sim, be right with you. Your favorite part. Okay. Let me do a screen share. All right. So the idea is I'm going to pick this up at some crazy angle here, and then I'm going to run this thing. Zoom, you can see that all right, I hope, right? Thanks. So as this thing swings back and forth, we're just trying to analyze. Let's do this in slow-mo. We're just trying to analyze the first swing as it goes from here to this point, to this point, to this point, to that end point. Okay, I'm going to bring this back over here to start. So right here at, so we'll call this point A, point B, point C, point D, and point E, all right? So let's think. How much centripetal acceleration is there over here at this first point, point A, at that first point? How much centripetal acceleration do you have? What do you think? Anybody, take a guess. It's okay to be wrong.
Some trig stuff with.
No. What's the equation for AC? Good guess. You would think it's complicated. Turns out it's not. What's the equation for AC? R omega squared or V squared over R, right? You release this thing from rest. What's the V? If you release it from rest, what value is V? 0. Isn't that cool? So you'd think it'd have to be some complicated SOHCAHTOA. I don't like my life. No, it turns out it's just 0. Now, what does tangential acceleration mean? It means change in, not velocity, but change in speed. So the centripetal acceleration relates to the change in direction, Peter. The tangential relates to change in speed. So you could think of AC as changing the direction and a tan as changing the speed. So in this case, is the speed going to remain 0 or is it going to change? It's going to speed up, going this way, tangent to the circle, right? So that's, and I'm just going to call it A subscript T for now so I don't take all day. All right. What do you think is going to happen at point B, the next point in the motion? It's going to speed up. Okay. So is AC going to be 0? Which way does AC point? What does the subscript C stand for in circular motion? Center. Towards the center. Does that make sense? Is this helping?
Is that okay to think about it like, yeah, as it's speeding up, it's pulling inwards more because it's pushing force out more?
No, that's not good. I'll explain that in just a minute. Right. Think about this. You got a ball on a string, right? I don't want to stop the screen share, but how much can you push on something with a string?
Which is the fictional.
No. I can't. Look, I'm going to push on this guy's face with a string, right? I can't push on him with a string. I could pull with a string, right? You don't push with a string.
Right.
More on that soon. I promise to come back to that.
Yeah.
Okay. And we're going to focus on that all day long. This is the most common thing that people, you feel pushed to the outside, but actually you're pulled towards the center. Is that good?
Yeah, I get it.
All right. Okay. A tan. Do you think it's going to be bigger, smaller, same size? What's your gut tell you? Why do you say smaller? Okay. What happens at the lowest point? Once you pass the lowest point, are you speeding up or slowing down? So we know you're speeding up here and you're slowing down here. You're slowing here. You're speeding here. What must be true at the very bottom? AT equals 0 right at the bottom. Excellent. Think about that. Right at the bottom is when you change from speeding up to slowing down. So right at the bottom, A10 is 0. Is that good? So then, I think that was Alonzo was saying, do you agree A10 is still tangent to the circle, but it should be a little bit smaller, right? Good with that? What about at the bottom? What's happening to AC at the bottom? Is it going to be, which way does AC point? Straight up, which is towards the center. Do you think it's going to get bigger or smaller than its previous value? Why? Gravity, as you go downwards, what does gravity do to you? Speeds you up. AC depends on speed. So this should be really big, right? How are the arrows going to change for those last 2 points? It's going to be a mirror image. AC is going to, it's going to slow down. So AC is going to get a little bit smaller. A10 is now working against you. Sorry, I'm so slow. And then right up here, what's AC at the top when you come to rest? 0. So right at the end points, there's no AC, but A tangent is a max. This is complicated, isn't it? This is why we don't cover circular motion on day 1. This is why you bust your ass trying to get all this stuff figured out. All right, you ready to see what this looks like? Let me stop annotating. I'm going to show the velocity and the acceleration on here. Actually, let's start with just the acceleration. Here it goes. Watch it. Right at the bottom, it's straight up. At the left and right edges, it's tangent to the curve, and we see it's doing this weird kind of angle. Do you agree that agrees with the arrows we have drawn? Is this helping you get a feeling for what this is like? Yes?
Is this A total?
The yellow arrow that is shown on the center of the cylinder as it wiggles around is A total. Correct. So notice, if I could, let me do this. Let me annotate. That is RA total here, and that is RA total there. Excuse me, you know what I mean? So if I could pause this while it's running, see how that kind of looks like what we drew at the bottom? Pretty much straight up. If I was perfect, I would have paused it right at the right spot. Tangent. Good? Now, I got to throw some mad props out to Alan, because the other day I said, hey, can you figure out this code for me, please? So let me show you something that Alan worked up here. And I know this is a little bit hard to see. This is a ball on a string. Ooh, I need to make this a little bit smaller. So what Alan did was he made these buttons so you could show, look at just the centripetal acceleration of a ball on a string. Notice it's pointing towards the center here. And it gets bigger at the bottom, and we see it getting, so this is the example of a ball that's going around over and over. It's probably going to stop here. Let me do this. Hey, why don't we give Alan a round of applause here? There you go. Let me just change this to 50, so I've got more time to talk. All right. Can you see that all right out there? When I run this, can you see the arrow okay?
Yep.
Okay. Let's watch this again. Now I'm going to show just the tangential acceleration. Look at this. It gets small, it goes away. Can you see that at all? Notice at the very top and the very bottom, the yellow arrow goes away. Can you see that at all, or is it too small? Right? It's a lot. This is the real physics of a ball on a string as the ball speeds up and slows down as it goes all the way around in the circle, right? So what about the tension? right? Look at the tension here. Let me get rid of that tangential. Look at the tension in the string. Watch it carefully as it gets to the very top. What happens to the tension? It goes away. If there was any less tension, this thing would fall apart. And we actually have a plot of it down here. Look at this first plot right here, this plot right here. Notice the tension is oscillating, but do you see that's not actually a sine wave? Do you see that? Look carefully at that plot. The peak is tall and skinny, but the trough is wide. So it's not, this is complicated. Like you were saying, it's some complicated relationship to the trig functions, but it's not a trig function itself. All right, let me go back up. And then look at the total acceleration, right? So gravity is causing it to speed up on the way down. Then when you get right to the bottom, they're both straight towards the center. And then as you go up, gravity is causing it to slow down. It's a very complicated set of motion. There's a lot of understanding you can learn from that. Let's just throw them all on there. Whoops. You can try and see, let me see. Notice here you can see the two components of acceleration. There's the red arrow towards the center. That's a centripetal. And then the yellow one is the tangential. All right. Is that enough on that? Are you getting used to that? It's hypnotic, isn't it? All right. I guess I shouldn't have dropped acid. Let's get back to work. In particular, let's understand the physics of this 6.52. Let's do the math of a real physics problem now. 6.52. Nice job, Alan. Was that worth it to see that or not?
Yeah.
All right, Alan, you did a good job. 6.52, get it fired up. It's impossible to show you that stuff in real time because the ball has to swing so fast, right? So hopefully that gives you a feeling for what we're about to do with that. Hopefully I didn't spend too much time. $6.52. Finish this damn ball on a string. What's my mass? Was it 0.2?
Yes.
Yep. What's the length? Thanks. And the velocity was 5. And the angle at this instant in time was what, 30 degrees? All right, sig figs, who cares? Whatever. We're just trying to draw this picture. That's kind of small. Sorry, my circles aren't that good. That's approximately the center. That's approximately a 30-degree angle. And I think I used a star in this problem just for fun. There we go. Feeling great. We're told that this angle, it's easier for me to label things algebraically. I don't know if you've noticed that. So we're going to stick to that. And I think I said the ball is moving this way. So I like to put the numbers separate and label the picture algebraically. I apologize if you don't like that style. That's just kind of how I got used to doing it. Yep.
Should switch the camera over.
Thank you. I am on the wrong monitor. That is good. Thanks, dude. Sorry about that. Oh my gosh, this simulation's still going. Whatever. All right. All right. This is the situation we're trying to analyze. 1 split second of that ball on a circle. Any ideas of things we could do to try to analyze this motion and learn about it? Anything that you can think of that we might try to do? Is the acceleration constant? What did we just see in the simulation? Was acceleration constant or was it changing all the time?
Changing.
So are we going to use constant acceleration kinematics for this? No way. Any other techniques that we've learned in a physics class that we might try to attack this with? Free body diagram. All right, I'm game. FBD. Give me one force acting on the star or the ball or whatever. I heard mg. Maybe I didn't. I hope I heard mg. What else? AC is acceleration. Is AC a force? Nope. It relates to force. We're going to use that, but it's not a force. Give me another force.
Tension, maybe.
Tension. Do you push with a string or do you pull with a string? So tension is this way. Now we could draw some coordinate systems, right? From experience, I know we want to use the coordinate system that's rotating with the ball. So imagine my hand is like, instead of XY, it's R and theta, right? R hat is outwards and theta hat, like this. This is going to be useful. Now I'm going to do something really weird. I'm actually going to use towards the center and tangent. Right? So instead of calling them X and Y or parallel and perpendicular, I'm going to call this towards the center and tangential. If you are passionate about understanding coordinate systems, the last couple pages of this book will tell you. But please, for now, let's just roll, okay? Is this ball accelerating? I'm going to draw this coordinate system here. We've got a tangential direction and a direction towards the center. Is this thing accelerating as it goes around? What do you think? The ball on the string. Was it speeding up and slowing down and doing all kinds of stuff?
Yes.
Yes. Is there a component of acceleration towards the center?
Always.
Yes. So there's going to be some AC. On the way up, is gravity speeding it up or slowing it down on the way up? Slowing it down. So what does that tell us about the tangential? Is it going with the motion or against the motion? Against. So we see it's going to look something like this. Now, and I should be careful here. Did you notice in the simulation that A tan was usually a lot smaller than the other one? Did you notice that in real life? So I'm going to try and make this look more like that for reasons I think that are crucial. So we might expect a lot of centripetal and not much tangential. So A total might look like that. And I want to point out, just look at the pictures I drew. Does this angle have to be exactly the same size as that one? What do you think? What's your gut tell you? Look at the picture. Do they look exactly the same?
They look pretty similar.
They look similar, but they're not exactly the same. Yeah. Remember in the simulation that we just saw, sometimes they were off at like 45-degree angles. So one of the most common mistakes students make is when analyzing this, this is almost never the same as theta. You would have to have an extremely unusual problem for this angle to equal theta. It almost never happens that I could think of. Maybe once or twice per circle it should equal it for one instant, and that's it. In general, don't assume this angle is the same as that angle. Is that enough on that? All right.
Would that be feet?
What's that?
Yours would name it feet. That angle.
Wait, say one more time.
So that angle, you'll name it B.
Yeah, you could name it phi if you want. You could name this phi in there. Yes, absolutely. Is that what you were saying? Yeah, yeah, absolutely. And then this is kind of off to the side. I'm just going to label it here. All right. Which force vector needs to be split into components before I write the force equation? Which force vector needs to be split up? mg. Watch what I do and tell me if it's right or wrong. Is that good or bad? Bad. Let me ask you, should a component be longer than the vector itself? No, this is not right. Is this parallel to my coordinate system? No, that's a problem. That's the most common mistake people make. Now it's looking better. It might not be perfect. The hypotenuse should be opposite the right angle, should be the original vector. So basically, the original force vector should always be opposite the right angle. Good enough? Help me out. What do you think this angle is?
How is here?
That one is theta. Take a look. Isn't this one right here theta?
Yeah.
What's this one? So what's left for that one? Did that help? This is part of the reason we beat you to death with inclined plane problems, is so that you get used to dealing with some of this geometry. So far, so good? All right. Who's feeling brave? I need the sum of forces in the centripetal direction. Again, most textbooks don't say centripetal, they'll say radial, but whatever. We know it's basically the same kind of thing. Give me one force in the centripetal direction. T, all of it or some of it? Positive or negative? Positive T towards the center. Good. Somebody else. What's another force towards the center?
Positive mg sine theta.
Yeah, mg sine theta is also there. Do you see that? Nice. Good job. Are there any other forces towards the center? No. What is this equal to? Okay, which acceleration? Is it a tan, a total, a c? Is it plus or negative? Which component lines up with towards the center? According to this picture, is it positive or negative? Positive. Don't overthink it. Done. Now you may be saying, what if I had used the radial coordinates? I could discuss that with you on the break, but it works out. If you call that way positive, do you agree everything would be negative, negative, negative? And then you get the same equation. That's why I was saying it doesn't really matter if you want to use radial or center. Okay. All right, finally, let's do the sum of forces tangent to the circle. Okay. What's the force tangent to the circle?
Minus mg cosine theta.
Negative. We call this way positive, this way, so it's negative mg cosine theta. So far, so good? How do you know why I'm spending all this time doing these angles with the verticals? Because in the real world, we use them. Finally, a real problem where we can use these. Yeah, okay. That's the only one. What's this equal to?
Negative m times a tangential.
Why did you stick the negative on there?
Because it's facing the opposite of
The
tangent.
coordinate. Yeah, we call this way positive. So depending how you draw your picture and how someone else draws your picture, we may have some discrepancies here. In the end, the magnitude should turn out the same. This is why it's so important for you to draw a coordinate system and label your stuff. That way I can follow you. Do you agree out of all this? Look at this one. We just figured out something. Now think about this. The minus signs cancel, but look at this picture. We found out that A tan, which is the size of this arrow, is G cosine theta, and it's directed opposite the motion. Right? Let's do a quick table here. Theta. Give me a sec. Okay, help me out. If we just plug in different angles into here, when you plug in 0 degrees, what is cosine of 0? What's that?
G.
Oh, well, cosine of 0 is
Oh,
1, so
one.
yeah, A tan is G. Is that what you meant?
Yes.
Yeah, I agree. So he's saying cosine of 0 is 1, so when I plug in 0 degrees, I get A tan is G. Good. What about when you plug in 90 degrees? 0. Where is this? Top of circle. Notice there's no tangential acceleration at the top, just like we saw in that simulation. Well, let's skip to 270. That's also 0, right? That's at the bottom of the circle. Again, think about it. This is 0 degrees. This is 90 degrees. This is 180 degrees. This is 270 degrees. Is that helping where I'm getting these numbers from? If theta equals 0, it's G straight down. Well, what is it when I get negative 180? Oh, sorry, not negative 1. What is it when I plug in? Oops, what's the answer?
Negative G.
Sorry, my bad. Now, wait a minute. This seems confusing. It's negative G opposite the motion. Do you agree that's the same as positive G in the direction of motion? Said another way, look, on this side, you're moving upwards with speed v, but your tangent, well, with some, how about I say v left for this side, because it might not be the same as this number, right? And your acceleration down here, you got A tan equals G downwards. Now, when we rotate the coordinate system, we're saying A tan, whoops. Over here, A tan is, let's see, negative G upwards, right? Think about it. We're saying opposite the motion with value negative G, that's the same thing as positive G downwards. Agreed? Oh my gosh, this works, but this is kind of confusing in my opinion. We see that the math does work out, but you have to do a lot of thinking about coordinate systems. Agreed? Is that enough on the coordinate systems and the angles and stuff for right now?
I feel like this would be proved on a test.
Yeah, well, typically what I might do on a test, if I was giving this as a test question, I might say, give me the tension and the strain and give me the size of the total acceleration. If I did that, let me ask you, could you get tension and could you get a total? The magnitude. Well, let's think. This is a little bit easier because this is A tan squared plus A centripetal squared. Do you agree you could do that? And then we don't have to worry about minus signs. How can I get T? No. Wait, what's AC? V squared over R? Don't we know V? We know R. So on a test, I might try to ask you simpler versions of this. For this first one, I wanted to really just show you the right way to do it in its full complexity. And then you'll see the rest of the problems we do today will be a lot more fun. And what we'll do is we'll simplify these in many ways. I try to avoid giving problems with tangential acceleration on test 2. We usually talk about this again in chapter 10, and I focus more on it then. Good enough for now? Yeah. Other questions on this crazy problem? Do that one at home and finish it out because there's a lot to be said for it. And then I would like to do 6.53 before we take the break, just to kind of, that's the last of the boring definition type problems. So let's look at 653. Any questions before I change boards and go on? Oh. I think this stuff is cool though. I don't know why.
I feel like this is like a sneak peek on how the world really works.
Well, machines, right? A lot of machines tend to convert rotational motion into linear motion and vice versa, right? You think about how a drill works, or how, like the classic one is, think about a train, right?
Yeah.
You got these wheels and you have a piston that causes a wheel to rotate. I mean, there's a lot to be said for interrelationships between linear motion and rotational motion.
Yeah.
It's massively important in mechanical engineering, building working equipment. So yeah. All right, that's it. Let's crank here. 653. And then we'll take our break. We got a circle. We got some ball on a string here, or whatever. We're going to assume this one somehow goes at constant speed. And I'll show you a cool trick here. Come on now. And Peter, I think you want to go that way. Just a little bit. You just scoot over one seat. Yeah, okay. Just for a few seconds. Take a look. Oh, sorry. Whoops. Look at this thing right here. Is this on? The whole thing?
Just off a bit at the bottom.
All right, you get the idea though, right? Let me see if I can. All right, that's close enough. It's not the whole thing, but the idea here is, here's an example. Do you agree this thing's moving at approximately constant speed? So as opposed to the ball on a string here, right? We were just talking about the ball on a string. We know it speeds up on the way down and slows down. Wait. This thing changes speed as it goes up and down. How about I say it like that? Because I'm tired. Yeah. Right? Whereas this one, you can see this is moving at approximately constant speed. So it is possible to make objects rotate in a vertical circle at constant speed, basically as long as they're balanced with their center of mass right in the middle. So far, so good with that? So let's pretend somehow we have a device where that's happening. Okay? Let's go back to the board. Whoops. What's that? Oh, yeah. Notice it's not quite centered. Do you agree? You see this thing isn't quite centered. It's probably the heavy side, that side, right? It's pretty close, though. It's pretty close. All right, whatever. Let's get back to this. So we're going to assume constant speed V, radius equals R. And here's something that we know. If constant speed distance equals rate times time. What's the distance all the way around the circle? That's the time all the way around. Who was the roundest knight at King Arthur's table? Circumference. Ouch. Sorry. Okay. What do you agree the distance around is 2 pi r? One time around the circle is 2 pi r. What's the name for the rate? V. What's the symbol we said we were going to use for period? You remember? That's double T or just basically T. Can we solve this thing for T really quick?
Yeah.
What do you get? Period.
What is it called, by the way?
Double T.
Oh, this is if you're using like called double T.
Okay, just double T.
If you're writing it in the equation editor, it's called a double T
Alright.
/ double T. But yeah, it's just sometimes that's called double strike.
Double strike.
But I don't know.
Sounds
I'm not an expert in it. Let's just call it T.
Yeah, T.
Period. But yeah, I only do it because you agree in a lot of these problems, as we just saw, capital T means tension, and I don't want to get it confused.
Yeah.
Little t means time. Okay. What the heck was the answer?
2 pi r.
2 pi r over v. Make sure I don't flip it. How can we, oh geez. How can we make sure this looks right? What can I do? Check the units. What are the units of r? Radius is in units of meters. What's the units of v? Meters per second. Cross multiplied by seconds over meters. It looks good. All right, so that's the period. That's question A. So if you're curious, how would I get the period? Well, if you have a problem where it's moving with constant speed, there you go. If you want the average period, right, you can put in the average velocity. That would work too. What's part B? Rotation rate. Part B. Told you we'd come back to this one. I want you to think RPMs. Actual units are what? Usually. Do you remember? Radians per second. Excellent. Omega is 2 pi over the period. Well, let's just plug it in and do the math. You can erase me. Whoops. It's 2 pi all over, what was it? 2 pi r over v. Right, just flip the reciprocal. So it turns out omega I memorized this in another way. It's also written on your equation sheet another way. Look, V is not your omega, it's R omega. Okay, if it works, it works. If it doesn't, sorry. V is R omega, all right? Let's check the units really quick. V. Radius. What did we say were the units for this sucker? That's why we have to use radians per second, not RPMs. Radians are unitless. This is why we have to use radians. Does that make sense? Now, okay, what else? Okay, let's do this. Part C. It says something's rotating at 10 RPMs. If I tell you 10 RPMs, what symbol is 10 RPMs? Rotation rate. What is the symbol for it? Omega. It's not a W, it's an omega. All right? To be clear, that's a W. Sharp pointy. Curvy is an omega. If you call this W, I'll know what you're probably talking about, but I'm still going to call you on it and say, hey, remember, you got to call it the right name, okay? You'll get used to it in a while. Now, what do RPMs mean? Revolutions per minute. Help me out. How does 1 revolution relate to radians? If you go 1 revolution, how many radians?
2 pi.
2 pi rad. 1 minute is 60 seconds. Let's do it. Out of board. Okay. Now I know this seems a little bit silly, but let's punch this in. Anybody got it? There's one little thing I want to tell you about this. Four nine. Is that right? That's what you got? I only know it because we did it earlier today, but yeah, that's what you got? Okay, thanks. Appreciate it. Now look, believe it or not, this is one of the most commonly missed unit conversions that I have seen, especially when you're going from rads to RPMs. What happens is when you're going from rads to RPMs, people say times 60 divide by 2 pi, and they forget the parentheses around it here. Around it here. So let me just tell you this. Look at the numbers. You agree it's about a factor of 10? So just remember that. When you're doing this conversion, say, look, when I'm going from RPMs to radians per second, is it about 10? And it's either multiply by 10 or divide by 10 with a little bit of garbage on the end. That's because 2 pi, that's 6.28. 6 over 60 is about 1/10. It works out pretty good. Good enough? So just when you're doing these conversions, check and see. Now from there, I think the rest is pretty easy. Ready for that break? Let's take your break. I'll erase the board. And obviously you should finish out the little bit of this problem, 652 and 653. I think there's a couple pieces we didn't finish, but yeah. All right, let's take that break. 5:44. Intense. All right. So I want you to briefly look at problem 6.54. That's basically this problem right here. Kind of looked at it a little bit. I'm gonna scoot this back for just a second here. We're not gonna do this problem right now, but I just thought I would show you what we're talking about and show at least a couple of aspects of this problem that I find interesting. So in this case, you can imagine this thing's rotating. And again, you can imagine lots of fair rides that look like this, right? The big wheels with lots of chairs on them and such. And one of the things that's interesting is you can imagine at one point, if I whip this thing fast enough, well, I guess that's sorry for that person. But look at the angle of the ball here. Do you see that? It's kind of complicated and changing all over the place. Now, if I can do this a little bit more smoothly. Sorry about that. See that thread count? That's what we were just talking about. Hopefully that person won't die now. Whoops. Let me just get this thing rolling. This is the other thing that's complicated about this. If you give it a sudden jerk like this, you get a lot of that bobbling. So I'm going to try and speed this up slowly, gradually. And you're going to hear me say this a couple times today. When we speed this thing up gradually, which component of acceleration is approximately zero? Which component related to the speed changing? A tan. So if I speed it up gradually, A tan approximately zero. That's going to come up over and over again. But I'm not very smooth, am I? All right, so we see this thing all over the place. Do you agree? What I'm trying to point out is at any one instant, we might have an angle here. And so it's possible you could get forces in different directions here. So when you're doing this problem, or if you do this problem, just watch out for that. There's forces on the rider, not only up and down or left, right, but possibly both. Got that? So that's all I'm trying to get at there. And so if you want to, you can look at that solution later. I need a volunteer. Peter, you want in? All right. Let's go over here. We're looking at problem 6.55. All right. So let's go over it. Then we'll go on. I'm not sleeve here. Are we? See what you still want to stand right about here. Okay. All right. So we got some water here. Now the idea here is, once you put that cup of water on this thing, I want you to swing it around in a vertical circle. Got it? So obviously, if we just go like this, it's not going to spill, but I want you to spin it around and around in a circle. Now, do you want me to show you the tips?
Sure.
Or, okay, why don't you step over that way for just a second? So when you're doing this thing, you kind of rock it, and then just go for it. Now, you don't want to go super violent on this one. You want to kind of gradually increase it and then just say, you know what, I feel good. I'm just going for it and just start swinging. And then keep swinging it and don't stop. Now, when you need to stop, that's where it gets really tricky, right? So you kind of got to do the opposite. You got to go around once and then just kind of go up about a third of the way, right? Instead of just trying to stop it, you got to go. Got it? Here you go. All right, let's see him do this. So just kind of rock it, and then just go for it, and keep it spinning.
Okay.
All right, now try to stop it. Let's give him a round of applause. Very good, very good. Nice job. All right, isn't that fun? Let's talk about this demo. 6:55, board 5. Isn't that a fun one? Yeah.
Did you know how to build it?
What's that? Oh,
Anyone ever spilled it?
every time. Like, we got towels over here, I was assuming. Most people spill it. And right, it's practically, do you agree it's pretty easy to get it started? Stopping it takes a little bit of finesse. So that's what happens. We used to do kids' science shows and let kids go nuts, and they basically just throw water at everybody. It was pretty fun though, right? They just like whipping it around. All right, so in this case, we've got the bucket of water or the cup of water or whatever. So where are we most worried about the water falling out of the cup? At the top. So I'm going to draw a chunk of water. So that's the water. To be clear, you can imagine here's the cup, right? What pushes the water against the cup? Nothing. The cup pushes the water towards the center of the circle. Do you see the subtle difference? You're right. You were right not to say anything. Right? The water is pushed towards the center. Think about it. Just before the velocity is going up. Just after the velocity is going down. Whoops. Which way is the acceleration at the top of the circle? Towards the center. We don't have a tan. Okay. So in this case, great. Now I'm going to go even further on this problem. We're going to make an approximation just to get this problem done. And I haven't told you how big really big is, but think about this. If V is really big, if you're spinning this thing fast enough, it's going to speed up and slow down a little bit on the way up and down, but maybe in the third sig fig. So it's approximate, like let's say the speed is 5.6 at the bottom and 5.0 at the top. Okay, it's not constant, but it's approximately constant. Are you okay with that? Just makes my life a little bit easier here to talk about this. And so we can just take the average velocity as the approximate constant velocity of this thing. All right. What's a free body diagram of the water going to look like? Here's the water. Give me one force on the water at the top. Gravity, mg. Straight down. Now, what was the other one you were saying? A normal force from the cup, right? Which way? What is the cup doing? Is the cup pulling the water upwards or pushing the water downwards? Pushing it downwards. This is okay. What forces act left and right?
A10 was 0.
A10 is 0, so what's true about the net force left and right? It should be negligible, right? They cancel out, they balance, whatever. We're assuming there's no forces left and right. If they were, they're balanced anyways, if that's true. Okay, cool. This thing's accelerating downwards. Tell me the force equation. Which way do you want to call positive for this frickin' problem? Down, right? Everything's downer here. Give me the force equation in the centripetal direction, which is downwards.
mg plus mc.
Mg plus normal force from the cup.
Plus or equals m.
MAC. Okay. So far, so good? Now remind me, what's the equations we have for AC? What's one of them? V squared over R. What's another one? R omega squared. Did I tell you that or not?
Yep.
Okay. Right. Do you remember that V, it's not your omega, it's R omega? That's where I got that from. So notice V is R omega. AC is R omega squared. Check those units. Okay. Now, we're going to run into trouble if the water falls out of the cup. We want the min, what did I ask for? Min speed. Okay. So what's the minimum speed before the water falls out? Okay. You're supposed to know something when you see this in a physics question. You might not know it. So I don't know. Does anybody know how to approach this type of problem? If we're looking for the minimum speed before the water falls out, this is actually a fancy way of a physics person telling you something about one of these forces. You're on the right track. It has to do with the normal force. If the water is falling out of the cup, what's the normal force? How much is it touching the cup if it falls out of the cup? Zero. So this is the trick. Set the normal force of the cup to zero. That's the special value, right? Where gravity is just enough to cause the centripetal acceleration. Right? If you go any slower, well, I guess this wouldn't work. All right? This has to be true. So in this case, what do I get? mg equals MAC. What drops out? How do I get the velocity? I'm looking for the minimum speed. That's V.
AC for V squared over R.
We'll use the V squared over R in this case because it's asking about speed. It makes sense to use the V squared over R version. I get V at the top min equals square root of RG. What could I check? Units. Meters times meters per second squared. That's good. Think about this. If I use a bigger circle, I have to be moving faster. Otherwise, I'm not going to make it. So far, so good? All right. I feel like I've got to sneeze. I feel like my allergies are coming on, but whatever. Keep rolling. What was the point of all this? There might be some point here. Oh, if we know this speed, could you also get the period? How would we get the period? What's the equation that helps us get the period? How does period relate to speed? 2 pi r over the period, right? So if we know this V, you could solve for this period. Good. Cool. Now I want to point out something special here. If we have a minimum velocity, this is our equation from period, for period. Is the period going to be a minimum or a maximum? If we have a minimum velocity, does that correspond to a minimum or a maximum period? Let's think about it this way. If you have a minimum speed, you're going slow. That's a long time to go around. Agreed? Your minimum speed, long time to go around. So a minimum speed corresponds to a maximum period. The maximum time to go around corresponds to the minimum velocity. Or said another way, right, it's inversely proportional. So if you solve for the period,
Any more time than that for to spill the water?
that's right, that's right. So we can do this calculation. We can get your arm length and figure out what's the slowest Peter could spin and then try and go slower and slower and then just spill the water everywhere. But it's pretty fun. We'll do that at the end if we have time. So far, so good? All right, here comes another problem. You ready? Read the next problem. Oh, whoops. Oh, I think we already talked about 656, didn't we? Oh, no, we didn't. I want to go over this really quick. I know this doesn't seem that important, but it's come up in a number of physics problems, so I'm going to talk about it. Oh, jeez. Look at this thing. I just want to point out a big difference between a ball on a string and a stiff rod here like this, or a piece of wood, or a pendulum that's solid. Now look at this. When we swing this thing at the top, if I go too slow, watch it projectile, right? If I go too slow, okay, we'll go really fast. I'm going to slow it down. See how it kind of launches into the air and does one of these things? You can see the tension go away, right? When the tension drops out, I didn't have enough velocity to maintain the circular motion. I didn't have tension in the string at the top. That's the same thing as the normal force going below zero in the cut. Whereas this one, if you have a stiff rod or some kind of rigid mechanism holding this up, notice you could get to basically zero velocity at the top. Do you agree? So just watch out for some physics problems. Sometimes what they'll do is they'll say, you have a ball on a string. Oh, well, then the minimum velocity at the top is square root of RG. If you have a rigid rod, what's the minimum velocity at the top? Zero. Just watch out for that. That's all I wanted to say. Okay. Now let's look at the next problem. The hell is the next problem? Gravitron? Okay. Give me a second. I think this is fun. Also extremely heavy. Okay. Got this thing here. I'll bring this back. All right. Hopefully you can see this okay. Wait, zoom? Am I on the wrong camera? No, we're right. Okay. Look at this thing. On the table all the way. Okay, I'm gonna pull back just a little in case. Nervous. Okay. You can see that hockey puck up there, right? Hopefully you can kind of see that. Now the idea is, what's holding it up? What force? Nope, AC is not a force. That's an acceleration. It relates to the force, absolutely. What's the type of force holding it up? Not a normal force. Which way does normal forces exert? Right? Perpendicular. Normal forces are exerted perpendicular. So it's not a normal force. What is it? Friction. Right? Have you guys ever seen the spare ride? Yeah. Right? Well, now, in this case, I'm putting my finger on here and slowing it down gradually. When I slow it down gradually, what is zero? A tangential. I'm changing the speed very gradually. Now, isn't this crazy how slow you can go? Now, at some point, it's going to slip, right? Oh my gosh, it's going. This is a really good one tonight. Any second now, it should drop. One banana. Okay, that took about 1 second to rotate. Did you agree? That's a very technical measurement, the one banana technique. Okay, let's learn about this. What we saw is, I'm gonna break something. Whatever. Okay, as we're spinning this thing, let's take a look at that. All right, where am I? Where am I? Where am I? This thing. Jeez, losing my mind up here. Can you see up the board with this in the way, or do I need to move it? Good enough for right now? All right. If I need to move it, just say, hey, I can't see, okay? What problem is this?
6:57.
6:57, all right. At least that's not the time. Okay, here we go. We got this crazy ass room. We got this barrel. And this is supposed to be a simulation of this person, but I'm just gonna draw a block over here. What's one force acting on the block? mg. What's another force? Which way? Perpendicular to the wall. What's another force?
Friction up.
Friction up the plane. Now, this is technically not an FBD, but I'm trying to get a feeling for it. So to be clear, this thing is rotating. So sometimes we'll use the symbol omega to indicate that it's rotating, right? Now, you're going to see me use this coordinate system for this one. Let me just redraw this over here. Strictly speaking, this way is not theta hat. Think about it. Theta hat is in the direction of motion. That's into the board, then out of the board. Theta hat is going around this way. So I'm just going to call this some other coordinate. I'll call it Z. This direction over here is towards the center. So I'm going to call that C. And now, which way is this thing accelerating?
Away from C.
When you move in a circle, right? Look at this thing right here, okay? Hopefully I'm on it. Screensavers, right? Okay. Which way does this thing exert a force on the hockey puck when it's sitting right there? Whoops, right here. Which way does the wall exert a force on the hockey puck? Pushes it. What's pulling it to the outside? Starts with N, ends with nothing. Nothing. Excellent. What's pulling the hockey puck? Nothing. What do walls do? They push. It's tricky, right? Got it? It's sneaky. Strings pull. Walls push. Got it? There's no force going this way. Which way does it accelerate? It wasn't moving up and down. Is it accelerating up and down? No. There's only one force, unbalanced left, right. Show me with your finger which way this thing accelerates. Yes. There's an unbalanced force this way. Said another way, towards the center. Got it? Towards the center. Did that help?
I'm still confused conceptually how it's still being stuck there. I mean, I get
You're
it.
used to riding in a car, and when you turn, you feel pushed to the outside. But you are not pushed to the outside. You tend to remain at rest, or an object in motion tends to stay in motion in that direction. And then the car says, no, move this way. So it pushes on you. When you feel pushed that way, you perceive that you move to the outside, but what's really happening is the car is saying, fuck you, go this way. Got it? Isn't that weird?
Yeah, it's strange.
Crazy. We're going to talk more about this in the next class because it's so crazy. Mruck you, go this way. That's what it was saying. Mruck. I don't know what that means. Whatever. Okay. It goes that way, right? Think about it. A second before, it was moving this direction. A second later, it's moving that way. It had to accelerate towards the center. Over and over. All right. Give me a force equation in the y direction, somebody. Oh, sorry, the z direction. I called it z this time. My bad. F minus mg equals how much acceleration do we have up and down? Zero, right? This thing's moving around and staying right there. So do you agree F equals mg? All right. What's the force equation in the centripetal direction? Somebody else. I'm going to leave a little bit of space. Leave like 2 extra lines. 2 extra lines. Sorry about that. What's in the centripetal direction? Okay. Now let's read the question. I want the largest period allows the block to remain suspended. Okay. I want the largest period. Largest. What frictional condition applies? Take a guess. Is it sliding down the wall? If we allow it to be suspended, is it going to slide or not? No. Large period. Is that fast or slow? Slow. Any slower, it's going to slide. What's the frictional condition? I heard static. Specifically, F equals what? You agree this applies? If we go any slower, the period would be so large that this thing would fall down. So we must be on the verge of slipping. Don't you love the wording in a physics problem? That's tough, in my opinion, to get that. You're supposed to know when you read this, oh yeah, that means that. That's hard. Well, wait a minute. All right. What are we supposed to find? What is it? What do we want? What do we want?
Period.
Period. Where does period appear in this nonsense?
PC.
AC has V, it has T, it has omega, whatever you want in it, right? How would we attack this problem to simplify it? What would Horatio do? Why is that convenient? Why is this marker so bad? Okay. What would Horatio do? Oh yeah. Got it? Out of all this, what do we get? I need to rewrite this crap. Looks like we get mu static equals G over AC. M's drop, the N's drop. Let's solve this for AC. G over mu static. All right. Well, somewhere in here, this is R omega squared or V squared over R, whichever way you want to go. And I know that omega is 2 pi over the period. Do you agree we could solve for the period somehow if we just did a little math? And I'm looking at the clock and I want to make sure I get to the next 2 problems, so I got to keep rolling. But I wanted to set this up and give you an idea of how you might approach it. So far, so good? You feel like you could plug in all this crap and solve for T? All right, great. Now, when we do this, actually, let's do this really quick. Let's do it. Race, go. So I'm going to move this around. I think I get omega equals the square root of G over R mu static. Is that right? So that 2 pi over the period. I want to make sure I didn't screw that up. Bring this R down, then square root, yes. So 2 pi over the period is equal to this. Now I'm going to flip both sides. That means flip the square root. That means the period should equal 2 pi times the square root of r static over g. Now I've got some numbers for you. Let's actually plug in the numbers. The radius. I don't know if you can see me measuring this thing on Zoom, but oops. This is, I'm going to go the interior radius. It's about 44 centimeters. Oh, wait, that's the diameter, right? 44 centimeters the diameter. So what's the radius in meters? The radius is 22 centimeters. What's the radius? 0.22 meters. Did I get that right? Am I off the board? I'm going to go back just a little bit, just in case. What's mu static? Well, let me ask you. Rubber. Do you think that's going to have a lot of friction or not much? Rubber on plastic. Oh, man, that's mu-y. That's a lot of mu right there. I'm going to say it's 1. Pretty close to 1 anyways. This might not be exactly true, but is it still on?
Yeah.
Okay. What's a good number for G? What are the units? Look at this. Meters cancel. Second, square root it. Dude. What do you get? What do you get for period? Punch it in real quick. What's that?
0.94.
That's about 1 Mississippi, if you ask me. Remember when we timed it very technically earlier? It looks about right. It takes about 1 second for this thing to orbit right after it's fallen down. It's not perfect. The coefficients aren't, but we get an idea that this is working. Feel good? All right. Fun question. Let's say we know that if the period is 0.94 seconds, so try and stay awake right now, okay? This is a fun question. Oftentimes it shows up on tests, some variation of it. It's usually only worth 1 point, so if you forget it, oh well, don't stress out. Let's say I spin this thing twice as fast, all right? So in this case, oh my gosh, come on. Oh my gosh. So much camera work. Whatever, there we go. All right, so in this case, we know if it's only rotating 1 time per second, it's going to fall down. If I go twice as fast, let's say the period's about a ½ second. That's about right there. What happens to the frictional force? I'm rotating twice as fast. Do I have twice the friction? 4 times the friction? What do you think? What were you thinking? Why is it the same? If I rotate faster, look at this equation here. We know that N equals M V squared over R. If you rotate faster, shouldn't you get more normal force? If you get more normal force, shouldn't we get more friction? No, why not?
In that corner, there's something different happening.
Right. Here's the trick. You're correct. I was trying to mess with you. Look, this applies only when it's on the verge of slipping. If you go faster, yes, you get more normal force. But we're no longer on the verge of slipping. This is not true if you go faster. You know what I'm saying? Is the free body diagram true? Yes. In fact, if you go twice as fast, what happens to the friction? Nothing. It still supports your weight. Not anymore. Fun question for you. Did the mass matter in this result here for the rotation rate? Did the mass show up? No. So they don't have to worry about kids versus adults on this ride. Now, here we do run into trouble. Different people wear different clothes. I'm going to go in there and I'm going to wear a suit made out of Teflon. And then my mu would be really slow. I'll be like, how come I'm not levitating? I want my money back. That would be a stupid thing to do, but you could do that, I suppose. Basically, so what they're gonna do in practice is they're gonna crank this thing up and get it going pretty fast. That way, different people with different clothes that have different coefficients of friction against the wall are still gonna be having a good time. All right, good on that? All right, let's do it. Oh my gosh, 15 minutes, we could do 2 more. This next one is one of my favorites. Which flies off first? Look at 116, talk to your neighbor. If you don't have a neighbor, think to yourself, I'm gonna get this ready. Oh. Okay. Take a look up here. Nothing up my sleeve. I don't know if you can see this. I've got some washers, and the reason we're putting different amounts of washers in here, right? I've got 1 washer, 2 washers, 3 washers, 4 washers, right? And so we've got the mass of these things. And the idea is now we can have objects with different mass, but they all have the same surfaces, so they should all have the same coefficients of friction. Agreed? Now I'm going to do my best to line these up perfectly. 1, 2, 3, 4. I didn't do a perfect job, but I tried to do the best I could. All right. My question is, which one of these is going to fall off first when I start speeding it up very gradually? As I speed it up gradually, do you think the light one's going to fall off first, the heavier one, or one of the middle ones? Take a second. Think about it. I'm going to erase the board and get ready to rock. Which one flies off first when I accelerate it very gradually?
If there would be a change in store, like it won't be like super hot or super cold, would that affect it as well?
What's that?
Like temperature? Would it?
Well, we're assuming they're all at approximately the same temperature. So hopefully that the change in temperature might actually affect the coefficients of friction or something. But yeah, we're going to assume they're all the same. It's not perfect, but they're approximately all the same. The other thing that's tricky is, right, hopefully they're all centered in these things too, right? But they're not perfectly centered in there either. But so it's not going to be a perfect demo, but it's pretty close from experience.
No, it's probably the opposite. You're all gonna go to the second.
Start flying up.
I'm just erasing the board on Zoom. I'm not writing anything if you're wondering. Okay, anybody have a guess which one's going to fly off first? Again, I'm going to very gradually speed this up, and eventually it'll be going so fast, we know they're going to fall off. Any guesses? How many think it's going to be the heaviest one? How many think it's going to be the lightest one? Couple. How many think it's going to be one of the middle ones? Okay. What else could it be? Let's find out. Let's do the math. Pick an arbitrary mass. Here's a block. I'm going to indicate clearly this is a side view. What problem are we on? 658?
Yeah.
Thank you. Okay. What are the forces acting on this stupid thing? Give me one of them.
MG downward.
MG. I'm down with that. What else?
Normal.
Which way?
Oh.
What force pushes this to the outside?
No force.
Nothing. There is no force pushing it to the outside. In fact, for it to go in circular motion, there needs to be a force towards the center. What force is that?
Direction.
Oh my gosh, that is good work right there. Which way is this thing accelerating? We said speed up gradually. What does that tell us?
Tan 0.
A tan equals 0, approximately. So which way is this thing accelerating? Towards the center. Give me the sum of forces in the z direct. Actually, let's do sum of forces in the center direction. Towards the center. Give me a force. F equals MAC. Forget the color coding. How about in the z direction? N minus mg, or N equals mg. If this thing's on the verge of slipping, what can I replace F with? Mu static times the normal force equals MAC. What would Horatio do? You guys are money. Does the mass matter? Look at that right there. That answers our question. The mass drops out. You guys did that pretty quickly. You should feel pretty good about yourselves. And I don't like to compliment anybody, so nice job. All right. Oops. Ready? Here we go. So if you care, this is, well, whatever. We know that we expect them to all go at the same time, right? Do you agree A tan is approximately 0 here? Pretty close to the same time. Agreed? Now, again, I could emphasize this. It doesn't matter where I put these. Look at this. I'm going to do this a slightly different way. I'm going to kind of stagger them so they're at different radii.
Except that it's like right in the center, right?
One of them is very close to the center, yeah. But if one of them is exactly in the center, yeah, you're right. Now let's look at this one. If I speed these up, it's not the mass that matters. It's the distance towards the edge. Do you agree? And that's because as you get towards the edge, what's the equation for AC? That's true. Give me the other one, because that's a hard way to analyze this one. When I'm spinning this thing, they all have the same omega. They all have the same rotation rate. So as you get closer to the edge, R is bigger, you need more friction. Those are the ones, right, that are not going to have sufficient friction. Closer to the edge, they fly off first. Pretty good? One last one, and then we're going to do more of these next time. And in particular, we're going to address some of these questions you've been having about fictitious forces. I have no idea what whiteboard we're on or where my Zoom is at all. Okay, that's pretty interesting, I think. Where's my, go 3 on this. It's up here. Oh man, this is just perfect. I'm just swinging around and hit students in the head. This is perfect. Oh my God, if only I could get put on administrative leave. Get paid. Can you see that a little bit better now? I don't know if this stands out at all. Let me put this a little closer. All right. Can you see there's a ball on a string here? Thank you. Oh yeah. Oh yeah. All right. We could see it just enough. And I guess I should zoom in a little bit. Thank you for your patience, everybody. Okay, and I can't quite see it because of these tables, so we'll just kind of. All right, now, this is not that cool, but it's important that you see it. Whoops. Now, this is supposed to be a ball going in a circle. It's not very perfect, but it's kind of circular there. Do you agree this is kind of tracing out a circle right here? All right. Notice this is a pendulum, but look at this. Do you see how it's kind of tracing out a cone? Look at the volume of space traced out by the string. So again, this is going around in a circle here, and it's tracing out this conical shape. This is called a conical pendulum. Look at that speed. Does that look constant or non-constant in your opinion? It's approximately constant. So one of the things that's tricky is when we do vertical circles like this, the speed is changing a lot. But in this kind of problem here, whoops, it's going to hit that. We can get approximately constant speed in this motion, right? So I think this is 665. Let's take a look at problem 6.65, and we'll do the banked curves and stuff next time. Conical pendulum 665. Okay. This is what we're trying to analyze here. If that gets in the way, let me know. 665. Losing my mind with all these markers. Kind of a hard one to draw, so I wanted to give you a feeling for it. I have some kind of string attached to the ceiling here. There's an axis of rotation directly under that string. And now the motion is actually circular, if I can get it just right. I'm trying to draw that. That's approximately circular. Okay. So to be clear here, this is the axis of rotation. The ball is going around in this circular path. We are told that this distance right here is L. And I want to be clear here. This is going to come up in lab. L is to the center of the ball. Okay. Now, typically when you're doing this, we measure this angle and call it theta. The angle to the vertical. That's just standard. Okay. When we're doing this, gosh, let's say I want to learn about this problem. What's something we could do? If I wanted to analyze this situation, what's something I could do in general? Draw an FBD. That's a great start. What's one force on the ball at the instant shown right here? Tension. Is it pushing or pulling? You pull with the string. What's another force? Somebody else. Mg, down. Is this ball was moving with constant speed? I think we said that, right? Is the acceleration equal to 0? What's that?
Approximately.
No. Maybe you meant an acceleration component is close to 0. Which acceleration component is 0? If a ball is moving with constant speed in a circle, is it accelerating? got this. Every force problem we did all day, there's an acceleration towards the. You're tired.
AC.
You guys did so good on the last one. You checked out, man. Do you agree this ball has to accelerate towards the center of the circle? Right? All right, we're almost out of time. Let me speed this up. Do you agree this is going to accelerate this way?
Yes.
All right. Now look, if this angle is theta, what's this angle?
I think I took it to geometry.
Theta by whatever rule. Got it. Excellent.
Yeah.
I just want to point out, this is going to be theta. What side is this? T cos or T sine? T cos up. T sine. Okay, let's do some force equations. Is there any acceleration up and down? Was this ball remaining in a plane? Yes. So what's the acceleration in and out of the plane? 0. So AZ equals 0. What's true about the ups and the downs? Yep, T cos equals mg from the z direction. What's true in the centripetal direction? T sine. I promise we're going to get you out of here as soon as I can. Just tough it out. If we wanted to analyze this situation, what would Horatio do? Why? The mass drops out. Good. All right. So you could get 1 over tangent or whatever. Now, wait a minute. There's one other piece here. What's AC? What's an equation for it? Give me one. V squared over R. What's R in this problem? That's what's different.
No theta.
Not changing.
This is from axis.
I'm going to draw a separate picture from my FBD. I'm going to do geometry on a separate picture. If this is L and this is theta, what's this side? L sine theta equals the radius. Got it? Now, I know it's time to go. We're at -1 minute, but I want to say a couple of things very briefly to have you, like, what is our takeaway from today? We're going to do more of this next time, but what is our takeaway?
There's trick, but sometimes there's not trick. It's tricky.
I was going to say this. If we have a problem with an object moving in circular motion, what did we pretty much do all day today? What was the first thing you did? Draw a free body diagram. What's the second thing? Force equations. Maybe you think of that as the same. And then we analyze, sometimes you need trick. Sometimes we need to look at the words of the problem and think, oh, is friction on the verge of slipping or not? But basically it's FBD, force equations, read the problem, solve for something. And we saw one of the things that's annoying is sometimes it's easier to understand the problem by thinking about V squared over R. Other times it's easier to think about R equals AC equals R omega squared. We know that V is not your omega, it's R omega. And we know that omega is 2 pi over the period. And we saw that all of these things sometimes show up. That's good enough for now. We'll do a couple more next time. We start chapter 7 next time. You need the next volume next time. Got it? We have to have work on volume 2 next time. Oh my gosh, that was intense. Let's give it up for Alan one more time for that cool sim he made. It'll be cool, Alan, making a conical pendulum simulation where you say trail equals true. I bet you could take the, we might have to work on that together. But if you want, you could try and do that, and if you have the time. If you get stuck on it for more than 3 hours, you better talk to me. But you can follow the sim that I made, right? And see the tricks that I did. In particular, didn't I make the code calculate tension for me? So now you know what you would do. You know FG, you know AC, you know V, you'd make the code using an FPD, right? So it should be the same. You'd have to put in a flat wall for the ceiling. Anyway, it's good. All right, is there anybody else that didn't get their test or anything? You get it? Yeah. Nice job, by the way. Nice job. Yeah. Mark, you too, right? You're gonna make it. All right. Yep, see it. All right, thanks, Angus. Oh, yeah, there's a class coming in. Question?
Yeah. I'm leaving out of town tomorrow. Would it be
Okay.
fine to do, I have internet access? Is it fine if I can do it on Zoom?
Yeah,
So last year?
The lab, no. Yeah. Now, if you're, because we're doing, I rewrote the lab because I was sick last week, so I changed it completely because I have to make sure we have time to do it.
Yeah.
But I don't know of any way we could do it online. Have you missed any labs yet?
No.
So then you can just do that as your makeup at the end.
Okay.
So at the end, there'll be a coding lab you can do in the last 2 weeks.
Mhm.
So you can just do that instead,
Okay.
and that's worth 10 points.
Okay.
And so the good news is I'm not doing the presentations now. So each lab you miss will only be equivalent to 10 points. So it should be totally make upable.
Okay.
Cool. And even if you don't make up all of it, if you can get like 6 or 8 of the points, that's pretty good. Good?
Yeah.
Okay, all right. Yeah, we're getting to the point where we need to use more specialty equipment. And this lab this week has a lot of specialty equipment. Yeah, that's all. Hey, I'll work on the board. Is that cool, Angus?
Yeah.
Ooh, what if I put the water spinner on here? I think you got a safe part. I get rid of it. Is that cool? Yeah. Get the water on there? Yeah. That's a safe thing. I like my ball on the string. I use this all the time. What do you think of that, Dom? Good. They did so well on that one question, and then, were you here for this?
Yeah.
I'm like, what? A equals 0? That's all right.
Yeah, well, it's 3D, so.
Yeah, it's harder.
Moving in a circle.
Yeah, I got this.
Everything's moving in a circle. Everything has a weight